Hello, everyone. I hope you're all healthy and well. Welcome to our next talk in our Golden Webinars in Astrophysics series. Our speaker today is Julian Barbour, who is an independent theoretical physicist and emeritus visiting professor at Oxford University. My name is Thomas Puzia, and together with Elisabeth Artutela-Villamoy, we have organized today's webinar for you. As you know from our previous webinars, we also have simultaneous language interpretation, which is provided by Mr. Patricio González, who is already simultaneously translating for us into Spanish.
En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comment on them. We will select the best questions for the discussion after the talk. Before we begin, I would like to briefly introduce our other panel members that are with us today. Of course, we have Julian as our speaker and Patricio as our interpreter, Thomas and myself as co-hosts and organizers. And from the faculty at the Institute of Astrophysics at PUC, we have Jorge Alfaro, that is a faculty at the Institute of Physics.
We have also the great pleasure of having the following panelists, our guest panelists who are with us today. We have Paula Reichert, who is a postdoctoral researcher at the Mathematisches Institut at Ludwig-Maximilians-Universität in München, Germany. We have Martin Harwitt, who is a professor emeritus of astronomy at Cornell University in New York. Then we have Gabriel Herceg, who is a postdoctoral researcher at Brown University, the Department of Physics there. We have also Flavio Mercati with us, Beatriz Galindo, distinguished researcher at University of Burgos, Physics Department of Faculty de Ciencias in Spain. We have Theodore Jacobson, who is a professor of physics at the Department of Physics at the University of Maryland. Then we have Julio Navarro, who is the Lansdowne Professor of Science at the University of Victoria in British Columbia, Canada. And we have Paul Heunigen-Hühne with us, who is a professor of philosophy, Institute of Philosophy at the Leibniz-Universität zu Hannover in Germany, and lecturer at the Department of Economics at the University of Zurich. We're also expecting Enrique Gomez, who is a professor of physics at Cambridge University, and soon Roger Penrose, who is Emeritus Roald Dahl Professor of Mathematics at the University of Oxford. And last but not least, we have also our Q&A manager, Simon Angel, who will be managing and sifting through the comments and questions for us today.
It is our great pleasure to introduce Julian Barbour as our Golden Webinar speaker this week. Julian studied mathematics at Cambridge and he started a PhD in astrophysics in Munich. But at that time, he was deeply interested in fundamental issues in physics and, above all, the nature of time. He then did his PhD on the foundations of Albert Einstein's general theory of relativity at the University of Cologne and got his degree in 1968. During his PhD, Julian came to the conclusion that time itself does not exist. He thinks that time is nothing but a measure of change and that physics had been developed under the assumption that time exists. After his PhD, he decided to become an independent researcher to pursue his long-term goals without having to suffer the consequences of a competitive academic environment that generally puts pressure on writing many articles. Julian has supported himself and his research without an academic position, working as a translator of Russian scientific journals. This activity gave him free time to develop a theory of time and inertia together with the Italian theorist Bruno Bertotti, with whom he brought his first paper published in Nature. This work led to 6 years of collaborations and ended in 1982 with a joint paper in Proceedings of the Royal Society of London, which is widely regarded as a seminal paper on the interconnection of local dynamics with the universe at large. This was the stimulus to the development of shape dynamics, which is a radical reinterpretation of Einstein's general theory of relativity.
Julian is also very interested in the historical development of ideas about time and motion. In 1989, he wrote his first book, Absolute or Relative Motion, Volume 1, The Discovery of Dynamics. In 1996, he retired from his translating work and has since then concentrated entirely on his physics research and on writing. He has summarized his ideas about the non-existence of time for non-specialists in his book, The End of Time, which was published in 1999. Although Julian has worked outside the academic environment, he has collaborated with several researchers in academia and is also the Emeritus Visiting Professorship in Physics at the University of Oxford. So now we would like to hand it over to Julian, who will introduce us to shape dynamics, the principles and possibilities of the radical unification of physics and cosmology. Julian, we're all ears.
Thank you. Hello. It is a pleasure to give this talk from my home near Oxford. If you can see the Latin tag, it means beautiful shape. Leibniz and Ernst Mach's objections to Newton's notions of absolute space and time are the inspiration behind shape dynamics. At the classical level, it identifies the dynamical core of Newton and Einstein's theories of gravity and a mystery in them. There is no relativity of size. Insistence on it, I will argue, could transform physics and cosmology. My collaborators and I have mostly used Newton's theory, especially to explore what the Big Bang might be like. We doubt whether general relativity's space-time gives a true picture. We recast Einstein's theory, making spatial symmetry fundamental and time a succession of spatial structures. Flavio Mercati's book gives much background detail. A lot of what I am going to say builds on what is in it and my own recently published book. Before I go on, I would just like to say, very regretfully, I didn't put down the name of one of my really very important collaborators. That was the Irishman Nilo Murukhu, who did very important work. But I just got an email earlier today saying that he passed away yesterday. So I would like to dedicate this talk to his memory. Here are some bullet points. Shape dynamics recasts and unifies physics and cosmology. Pure numbers define the fundamental entities, which are shapes. Distributions of particles in space illustrate the principles and possibilities. The set of all shapes, shape space, is compact and has an intrinsic probability measure. Its existence has surprising statistical implications. The theory's primary invariant, the complexity, has multiple properties and interpretations, some completely unexpected. It might even be time. Leibniz said space is the order of coexisting things, time their succession. Mach said that relative motions are alone determinable and time an abstraction from change. Minkowski either ignored or did not know these comments. His space-time is a void substance that makes time almost identical to space. Mach inspired Einstein, but Minkowski's space-time is still present as a glue that locally holds the world together in general relativity. Shape dynamics replaces the glue by difference of shapes. Dirac's comment, which you see at the bottom, brought him close to shape dynamics. Velocities are ill-begotten. Only dimensionless ratios, which are used exclusively in shape dynamics, have physical meaning. Observationally, the universe is not expanding, but changing its shape. Insistence on ratios seems minor, even obvious, but it is transformative. Angles, as fractions of a circle's 2 pi, are the foundation of shape dynamics. That observed ratios are the basis of all observations highlights an issue in cosmology. The universe is said to be expanding, but cosmologists can only observe ratios like redshifts. They observe differences of them, not differences of distances, which expansion of the universe seems to imply. An alternative framework for thinking about a changing universe is shape space. N particles have a configuration space of 3n dimensions, 3 of which locate the center of mass, 3 fix an orientation, and 1 the overall size. These 7 are absolute, or, as Leibniz would say, extrinsic. The intrinsic, background-independent shape depends on only 3n minus 7 numbers. The space of all possible shapes, shape space, is the quotient of configuration space with respect to the similarity group. Quotienting by scale to implement relativity of size is decisive. I think it could fundamentally unify physics and cosmology, transforming both in the process. Projection of general Newtonian solutions to shape space eliminates all redundant information and destroys none that is essential. History becomes an unparametrized succession of shapes that, by time reversal symmetry, carries no Newtonian absolute direction. The intrinsic degrees of freedom in shape space are 3n minus 7 that define a shape and 3n minus 8 that define a direction. The simplest, most predictive, most natural evolution law of a universe in its shape space is geodesic, with an initial shape and direction at it, the Cauchy data. That's the test a relational theory of the universe should pass. Newtonian theory does not pass the test because general n-body solutions projected to shape space require 5 additional extrinsic non-geodesic degrees of freedom. According to the velocity decomposition theorem, the kinetic energy decomposes at any instant into the amounts in change of shape, in rotational energy, and in pure dilatational expansion. They yield 2-dimensionless ratios. The direction of the angular momentum relative to the instantaneous shape gives 2 more. The 5th is the ratio of the kinetic and potential energies. In shape space, these are all additional degrees of freedom that evolve together with the shape. Their manifestation in subsystems of the universe, like the solar system, vindicates Newton's absolute space and time. However, in a Machian relational universe, the total energy and angular momentum vanish, but there can still be subsystems with all possible energies and angular momenta, provided they sum to 0 for the complete universe. In a Machian treatment, 4 of the problematic additional degrees of freedom disappear for the universe, but subsystems can still have all energies and angular momenta. What shape dynamics highlights is that to model a universe like ours, in which there is ongoing structure formation, the variable that in Newtonian terms is the ratio of the amount of kinetic energy in overall expansion divided by the amount in change of shape must be retained. Because it is shape dynamically inexplicable, I call it the anomaly or the creation measure, because without it, nothing interesting happens in a classical universe. I said insistence on ratios seems minor. I don't think it is. It may reveal the secret of the universe. It is easy to see where it hides. The orbit in configuration space of a Newtonian system with energy E can be found as a geodesic by extremalizing the action of Jacobi's principle. Lambda is an arbitrary monotonic parameter. The energy appears as a constant together with the potential energy. The reparametrization invariance of the action makes Jacobi's principle timeless. In fact, his aim was not to eliminate time, but merely to correct a mathematical inconsistency in Euler and Lagrange's form of the principle of least action. However, inspired by Mach, you could hit on that form of the action to create a timeless theory of the universe. The intuition that both time and motion are relational does lead rather naturally to equations with the form that one needs. The recovery of time and clocks in the form in which we know and use them is described in my archive paper, The Nature of Time. Complete elimination of the superficial resemblance to time through the use of the curve parameter lambda leads to Jacobi's own parameter freeform, shown here for the n-body problem, with vanishing energy and angular momentum, and with the explicit form of the Newtonian gravitational potential. Faithfully reflecting Mach's aphorisms about both time and motion, it involves only differences of separations between the particles. More important in the search for the secret of the universe, it highlights something Mach missed. The Newtonian gravitational potential in the Jacobi action is not scale invariant. The length dimension of the potential is -1 and does not balance the kinetic terms +2. The action is therefore not scale invariant and is what, in Newtonian terms, allows expansion of the universe. Its size at any instant is nominal, but one can say it is now larger than it was earlier, yesterday. This is due to the specific structure of the action, which is not scale invariant. It's the same in general relativity. There is just one Hamiltonian degree of freedom in the action that is extrinsic from a shape perspective. Another way of seeing this is that in the principle of least action in both Newtonian and Einsteinian gravity, it is necessary to specify a ratio of scales at the two limits of integration of the action. I will now introduce two shape dynamic concepts which hint how our universe might be creating structure without an extrinsic term in its action. I need a sip of water. Shape space comes with a dowry of two architectonic structures. The first is a relational natural metric and can be illustrated by the three-body problem. Its three particles must always be at the three vertices of a triangle. Newton's concept of absolute space allowed him to combine two quite different kinds of motion of the particles. Changes in the separations between them, but also simultaneous change of the position and orientation of the instantaneous triangle in absolute space. The action in Jacobi's principle is an amalgam of the two. In the figure, the dashed and solid triangles are nearly but not quite congruent. In A and B on the left, the relative changes are the same, but the absolute ones are not. The infinitesimal actions are different and give different non-vanishing angular momenta. However, one can define an action that depends only on the relative changes by best matching. Imagine, as in case C, that you hold in your hands the two triangles. Place one on top of the other and rotate and translate it until the positive definite radicand is minimized. This brings the centers of mass to coincidence and yields an action with vanishing angular momentum. The resulting Machian ds is a difference of configurations and an emergent time difference. It is not a glue. It would be very natural to go one step further and change the relative sizes. But the resulting action gives a model universe that classically cannot expand. Despite this apparent failure, it gives something that might be much more significant, namely a scale invariant difference of any two infinitesimally different shapes, and thereby the distance between them in shape space. It defines a purely relational natural metric. There's something else as well. The Newtonian configuration space is non-compact because the scale degree of freedom is unbounded. The quotienting with respect to it makes shape space compact. Then on it, the natural metric defines relative volumes. With them, measures and probabilities are automatically defined, providing a secure foundation for statistics and probability, which Maxwell called the true logic of the world. So far as I know, no similarly robust foundation for statistical arguments exists in standard cosmology or any of the approaches to quantum gravity. I think the argument for taking space as opposed to space-time as fundamental is supported by the fact that ever since Hermann Weyl's theory in 1917, there have been many attempts to create a four-dimensionally scale invariant theory. They have not led to definitive success or novel insights. I find it encouraging that our realization of scale invariance in space, as opposed to space-time, does look as if it leads to things that are both new and unexpected. This brings me to the second architectonic structure. It is a one-parameter family of structures which are subspaces of codimension 1 in shape space that the primary invariant of the similarity group defines. Tim Kozlowski, Flavio Mercati, and I call this invariant the complexity. Mathematically, it is the ratio of the root mean square length and the mean harmonic length of a distribution of particles in space. It's something purely mathematical. As a ratio, the complexity meets the shape dynamic gold standard of being a pure number. I'll let you absorb the mass-weighted expressions for a moment. Note that up to a factor, the numerator is the square of the center of mass moment of inertia, which is half the trace of the inertia tensor, while the other is, again up to a factor, the inverse of the Newton potential. Thus, the shape complexity is the ratio of the two most fundamental dimensionful quantities in the Newtonian n-body problem. It is a sensitive measure of clustering, especially for large n, because close approach of two particles has little effect on the root mean square length, but can greatly change the Newton potential, even making it infinite. This creates possibilities we never anticipated. The complexity has a counterpart in closed space vacuum general relativity called the Yamabi Invariant. The proof of its existence was a triumph of 20th century mathematics, but its properties, especially when matter is present, have hardly been explored, and certainly not in the manner we have started to use the complexity in particle dynamics. The complexity has an absolute minimum, local minima, and saddles. It has no maxima, only infinite singularities. The sphere you see represents the shapes of the simplest possible relational universe, which consists of three particles. You can't make shapes out of two or one particle. There's no angles there. They must always be at the vertices of a triangle whose shape is defined by two internal angles, which again are pure numbers. Each point on the shape sphere represents the shape of a triangle. Chiral partners are at the same longitude and opposite latitudes. Degenerate collinear triangles are on the equator, and for equal masses as here, the equilateral triangles are at the poles. The minimum of the complexity, shown by the color coding, is at the equilateral triangles, whatever the mass is. On the equator, there are three saddles named after Euler, who discovered their significance. The contour lines show the one-dimensional level sets of the complexity. In this simplest case, the probability measure that the natural metric defines is simply proportional to the contour length. I'm not aware anything like shape space has been explored in the quantum gravity literature. If, as Leibniz said, space is the order of coexisting things, the complexity of point particles in Euclidean space is the pure number that most directly quantifies the order. Behind it is the similarity group, which characterizes the fundamental symmetries of Euclidean space and plays three roles. It defines shape space, the natural metric, and the complexity. This slide lists four roles that the complexity plays even before we come to the one that, if nature works that way, trumps them all. For any number of particles, the complexity always has an absolute minimum that corresponds to the most uniform distribution the particles can possibly have. As defined, the complexity is a measure of clustering. That's much the same as variety. Things that are uniform lack variety and structure. Leibniz actually said, if I remember correctly, variety is reality. If we buy that, the shape with minimum complexity is at the absolute zero of variety, and with it, reality. For a shape now with variety greater than the minimum, the difference is the amount of created reality compared with the absolute minimum. The hint at an analogy with the absolute zero of temperature is not coincidental, though it is subversive. I will argue that for the universe, shape dynamics inverts all normal thermodynamic and statistical mechanical orthodoxy. Next, apart from its sign, the complexity is what the n-body specialists call the shape potential or the normalized Newton potential. It is simply the Newton potential made scale invariant through multiplication by the square root of the moment of inertia, which is the other key quantity in n-body theory. If the n-body problem is used to model an island universe, for which external rulers certainly cannot be employed, the dimensionful gravitational constant simply disappears, and the shape potential replaces the conventional Newtonian potential as the quantity that governs the evolution. This matches the first principle of shape dynamics. Only pure numbers formed as ratios of things of the same kind are truly physical in a dynamically isolated universe. The next interpretation of the complexity is a real surprise, given what I said about the ratio of sizes in cosmology being the last vestige of the Newtonian absolutes. The complexity is the ratio, as I said, of the root mean square length, basically the average of the large interparticle lengths, which can be identified with cosmological scales, divided by the mean harmonic length, the average of the short lengths, which are natural to take to be atomic scales. The operational meaning of measurement allows us to say that the latter measure the former. This means that the complexity is, almost paradoxically, the scale invariant intrinsic size of the universe. Every possible shape of the universe proclaims its own size. This makes it all the more puzzling, suspicious, I would say, that in the principle of least action applied to the universe, we need to specify a ratio of sizes that bears no relation at all to the intrinsic sizes that the two shapes already have. Hamlet would surely say there's something rotten in the state of cosmology. There's a related interpretation of the complexity. Its inverse is, in scare quotes, a scale invariant Planck length. The Planck length inevitably has a value relative to something in the universe. My hand, say. Its value tells us nothing about the current state of the universe, what there is all around me in my study here. If instead of my hand, we use the Hubble radius, we obtain a value of the Planck length on cosmological scales. That's better, but it still tells us nothing about the detailed structure of the universe out to the Hubble horizon. In contrast, the inverse of the complexity is the primary characterization of such structure. The smaller it is, the more structure there is in the universe, all the structure that you see around me. What is more, the value of the putative scale invariant Planck length is directly encoded within a single shape, whereas determination of the three physical and dimensional constants used to determine the Planck units requires a finite interval of time, and hence many successive shapes of the universe. Thus, the complexity hints at a unification, not of forces, but of fundamental concepts in physics and cosmology. Further support for this comes from consideration of entropy and the foundations of thermodynamics, which developed out of the study of steam engines. Critical for their operation is, of course, that the working medium remains in the cylinder. Otherwise, the train comes to a stop. This fact is reflected in a restriction made in all thermodynamic and statistical mechanical studies. They all assume the studied system is in a conceptual box, or more or less like a star, is self-confined. The size of the conceptual box may change, but it plays a crucial role not only in confining the considered system, but also in defining a meaningful length scale for coarse graining. Mathematically, statistical mechanics is the study of systems whose phase space has a bounded Liouville measure. Gibbs based his entire treatment of statistical mechanics on the conservation of the Liouville measure. The fact that the overwhelming majority of the microstates in the microcanonical ensemble belong to the macro state of thermal equilibrium is the reason why he, like Boltzmann, failed to find a dynamical explanation for the second law of thermodynamics. The picture that gives is bleak. Imagine a Maxwell demon riding on one of the particles in one of the microhistories of a Gibbs ensemble. Throughout its entire flight, the universe the demon sees resembles a swarm of bees. Nothing of interest happens in either direction of time. If, as is often the case, the potential that governs the dynamics is homogeneous of some degree, then in thermal equilibrium, the Virial Theorem holds, and the time average of the kinetic energy will be equal to the time average of the potential energy multiplied by some factor. The Virial Theorem in Newtonian gravity is particularly interesting. Here are the equations. The center of mass moment of inertia I measures the system's size and is the square of the root mean square length multiplied by the total mass. For a potential homogeneous of degree k, Newton's second law leads to the expression for I double dot. The Newton potential is homogeneous of degree -1, and this leads to the Lagrange-Jacobi relation. If the energy is non-negative, then because the Newton potential is negative definite, I double dot is positive definite, and plotted as a function of Newtonian time gives a curve that is concave upwards. As you see, here it is, its slope, the slope of the curve, which is equal to half of I dot, and may by analogy with angular momentum be called the dilatational momentum, varies monotonically in either time direction from minus to plus infinity. It is a Lyapunov variable. This means that Poincare recurrence, which makes a dynamical explanation of the entropic arrow of time impossible in a confined system, cannot hold in the n-body problem. In either time direction, d increases monotonically from minus infinity, imagine yourself going down that curve on the left, reaches the value 0 at the Janus point, at which the size has a finite minimum, and continues to rise to plus infinity. This behavior is a direct consequence of Newton's equations, provided only that the energy is non-negative, which includes the Machian case of vanishing energy. This slide justifies the coining Janus point after the Roman god who looks in two opposite directions of time and challenges thermodynamic orthodoxy. It has long been dogma that entropy puts the direction into time as an increase of disorder. Shape dynamics suggests that is wrong, and moreover, that there is no need to add some special state in the past, something inexplicable within the known laws of physics, a past hypothesis, in order to explain the arrow of time. We've seen that, provided only the energy is non-negative, a Janus point of minimal size must exist. The growth of the size either side of the minimum defines bidirectional arrows of time. However, in shape dynamics, size is unphysical gauge and is therefore not plotted in this figure, which shows much more illuminatingly what the complexity does. It is here that novel statistical effects appear in shape dynamics. As I said, statistical mechanics was developed in a conceptual box and accordingly restricted to dynamical systems with phase space of bounded Liouville measure. In contrast, the n-body problem is not in a box and lives, in conventional terms, in infinite phase space. What happens there is quite different. At just one point in solutions of the n-body problem, the system is, however, effectively in a box. It is at the Janus point, at which there is no overall expansion. At this one point, a nominal size common to all possible solutions can be specified. That effectively puts all the initial data in a box from which all solutions emerge bidirectionally with size steadily increasing relative to the nominal initial size. Boltzmann's breakthrough to interpreting entropy as a count of microstates was that, in the conceptual box he postulated, and for sufficiently many particles, the great majority of states have a uniform spatial distribution and Maxwellian velocity distribution. He identified them with thermal equilibrium states and showed that they are vastly greater in number than all other states put together. By exactly the same argument, this must, at least heuristically because coarse graining issues are always subtle in classical dynamics, also be the case at just one instant, precisely at the Janus point. Such a point necessarily exists in the n-body solutions with non-negative energy, including the ones with zero energy, as shape dynamics mandates. The figure from 7 years ago shows the complexity increasing either side of the Janus point. On the left in the three-body problem, on the right in a simulation with 1,000 particles, which averages out large fluctuations. The bidirectional arrows of time could be seen from the moon. This behavior happens in every solution. It is not a statistical effect revealed only in a Gibbs ensemble. Statistics is used only in the heuristic proof that virtually all individual solutions look thermal at the Janus point. An internal observer riding like a demon on one of the particles will necessarily be on one or the other side of the Janus point and will see something very different from the chaos in the midst of which Maxwell put his demon. Our demon will find an arrow of time that does not doom his universe to expire in the heat death of fire, but rather to indicate that it emerged phoenix-like from fire in order to progress to an increasingly ordered universe. This striking resemblance to the history of our own universe is a direct consequence of the shape dynamic approach. It overturns the conventional story. It is not entropy, but complexity that determines the direction of time. And it does it of direct dynamical necessity, not through an ill-defined past hypothesis. How is this, you will ask, to be reconciled with long-established thermodynamic facts? Now, they hold rigorously only in idealized, perfectly confined systems. But such things do not exist in the universe. They never have and never will. But transiently confined systems do have a more or less fleeting existence in the universe. You see them in the figure either side of the Janus point in the artist's impression of evolution from effective thermal equilibrium at the Janus point. Those structures represent galaxies, stars, the Earth, even you and me. All such subsystems are subject to the well-established laws of thermodynamics, including even black holes. A summary is here in order. In systems, either confined or unconfined, with a homogeneous potential, the Lagrange-Jacobi relation governs the behavior of microhistories. What each individual microhistory does is more revealing than a Gibbs ensemble of them. The ones that are confined are dull, the ones unconfined, interesting. In the n-body problem, they emerge from chaos and break up into clusters. I do not think you can call that an increase of entropy and disorder. There is no coarse graining scale to define an entropy, and the clusters become subsystems of the universe that, as they become dynamically ever better isolated, acquire energy, momentum, and angular momentum that are conserved with ever better accuracy. The bulk of the subsystems eventually decay into Kepler pairs and single particles. Each Kepler pair becomes a rod, a clock, and a compass all in one. With increasing precision, all Kepler pairs measure the same distance, tell the same time, and define consistent compass directions. Together, they realize a material frame of reference in which Newton's laws hold. In particular, the single particles move inertially. That looks to me much more like the creation of order than disorder. It is broadly similar to what we know of the history of the universe and is still consistent with the most basic thermodynamic behavior, since all such isolated subsystems can only exist if they have negative energy, and must therefore, as follows from the Lagrange-Jacobi relation, virialize before decaying in almost all cases into Kepler pairs and single particles. That's the essence of thermodynamics in the real universe. I think a particularly strong argument to reconsider what happens to the concept of entropy in an unconfined system is due to David Sloan. He points out that in dynamical systems in which the potential is homogeneous, there must be asymmetry, not of the kind Noether studied, but one due to dynamical similarity. It is well known that such a symmetry is behind Kepler's third law of planetary motion. Dave has shown that such a system leads to a focusing of solution curves onto attractors in shape phase space, which is an odd-dimensional contact space. I won't go into the details, which you can find in Dave's paper, together with a discussion in Sean Gribb's. The key fact is that the focusing mimics an effect like a special form of friction. For example, as shown on the left for a scalar field in FLRW cosmology, there is focusing onto an attractor of a Gibbs ensemble, not in phase space, but in shape phase space, which is odd dimensional. In the three-body solution on the right, the shape of the system in an individual solution is always driven to one of the peaks of the complexity, around which the curve circles in a limit cycle motion. That reflects ever more perfect Keplerian motion of two of the particles around each other, and ever more perfect rectilinear inertial motion of the third particle that escapes from them. That is already an impressive increase in the ordering of motion. It becomes greatly more so when there are many particles, for the asymptotic state then consists almost exclusively of Kepler pairs and single particles, with motions all remarkably correlated with each other. What I have said about the arrow of time is, I believe, secure. I now want to discuss the most radical possibility that shape dynamics has so far suggested. This is where things definitely become speculative and even seem a bit crazy. But I will present them because they do spring from what seem to be sound principles that have not hitherto been developed, and they do seem to touch on quantum mechanics, for which Niels Bohr said, one must have crazy ideas. What I have so far discussed is only one of two ways to model the universe. As preparation for what follows, note that in the 1,000-body simulations, in which the three-body fluctuations are largely evened out, the complexity increases steadily and more or less uniformly with Newtonian time. Because the fluctuations can briefly reverse its increase, the complexity cannot be identified with time in a classical theory. But look how straight that increase becomes. Could it be that in a quantum theory of the universe, the complexity literally is time? Could that be shape dynamics' trump card? One thing which suggests that it could is that the complexity has an absolute minimum, which could be identified with the birth of time, and increases continuously to infinity. Time will never end. Something else is important. In the figure, the moment of inertia, the size of the system remains finite at the Janus point. The heuristic argument for thermal equilibrium at the Janus point relies on it. However, it has been known for over a century that certain remarkable solutions exist in the Newtonian n-body problem, in which all the particles collide in one instant at their center of mass. They are called total collisions, and of course, at them, the Newtonian size of the system is 0. That has 3 profound effects. The first is that n-body specialists have not been able to find any way of continuing such solutions in a unique manner and have concluded that Newton's equations break down at total collisions. Flavio Mercati and Paula Reichert have been considering whether such solutions can be continued in a shape dynamic setting. I think such a continuation could be very interesting, especially if it also works at black hole singularities. But whether or not a continuation exists, I'm going to consider the implications of the fact that a total collision solution can, by time reversal symmetry, be transformed into a total explosion or a Newtonian Big Bang. It is interesting that the existence of such solutions was known several decades before expansion of the universe was discovered. For them, a curve like this replaces the Janus point curve shown earlier. You see a universe exploding out of 0 size. The second effect is that in 3 dimensions, the angular momentum of the system must vanish. Much more significant is that the solutions can only begin with a special shape called a central configuration. It can be either collinear or 2 or 3 dimensional, in which case the initial shapes are typically uniform, often remarkably so. In the case of 3 particles, the non-collinear total explosion solutions all begin equilateral. For 4 particles, one initial shape is the regular tetrahedron. In a central configuration, the force on each particle is directed toward the center of mass with strength proportional to the distance from it. If all particles are initially at rest in a central configuration, they will fall homothetically without change of shape until they all collide at the center of mass. The much more interesting fact is that non-homothetic solutions in which the shape does change can terminate in a total collision, provided the final shape is a central configuration. Particularly interesting from the point of view of shape dynamics is that central configurations are extrema of the complexity, either the minima or saddles that I mentioned. If the theory of time I'm going to propose is on the right lines, these properties will have far-reaching consequences. We can start with the nature of the minima. As I said, the complexity has an absolute minimum. At it, the particle distribution is as uniform as it possibly can be. That's manifestly true for the equilateral triangle and regular tetrahedron in the 3 and 4 body cases. As the number of particles increases, the lowest complexity distribution becomes incredibly uniform. A numerical study early this century demonstrated this beautifully. The image in this slide on the left is a central configuration of 500 equal mass particles with complexity very near its absolute minimum. On the right, there is a section through it. Interestingly, the near perfect spherical symmetry and constant density that you see in the section, out to the abrupt end in a rim, is a manifestation of Newton's potential theorem. The fecundity of the complexity suggests to me that it springs from the very heart of mathematics. I think you may agree with that claim when, in a moment, I show my prime exhibit. Central configurations have been of great interest to mathematicians for about 120 years. Stephen Smale has called them a problem for the mathematics of the 21st century. For the last 20 or so years, numerical studies have been finding more and more central configurations, but until very recently, only for a few particles, up to about 10, or, as in this slide, only at or very near the complexity's absolute minimum. However, in the spring of this year, Manuel Izquierdo, working with Alain Albouy at the observatory in Paris, started to find central configurations of 1,000 equal mass particles at somewhat higher values of the complexity. They are mostly in 2 dimensions, but the ones in 3, which obviously require much more computing time, are similar. As you will now see, they reveal remarkable structure only hinted at previously in the numerical examples with up to 10 particles. On the left is a central configuration very close to the absolute minimum of the complexity, or at it perhaps. It is like the section in the previous slide, round as a pancake with almost perfectly uniform density, except that in this case, I think because of the difference between 3 and 2 dimensions, the density decreases slightly until there is an abrupt end at the circular rim. The one on the right, with only marginally greater complexity, as you see if you look at the numbers, exhibits remarkable voids and filaments. As of now, Manuel and Alain have not been able to find an explanation for their form and existence. They are surprisingly like the distribution of the galaxies in the universe in its present epoch. However, I do not want to suggest a direct connection. I'm more interested in other facts at the moment. The first is that there are a simply extraordinary number of such central configurations. Alain estimates their number at n factorial, where n is the number of particles. That is a staggering number. In fact, it is not even known if the number is finite. A major unresolved problem is whether a continuum of such solutions exists. Alain and a Russian collaborator have shown that there isn't for 4 particles in the plane, and have almost proved the same for 5 particles. I will come back to some of the finer details of this image after I've discussed further the radical idea that the complexity literally is time in a quantum universe. In one sense, the idea is not radical. Bryce DeWitt recognized about 60 years ago that simple-minded canonical quantization of general relativity leads to a wave function of the universe that is static. I think Bryce was the first to suggest that time in quantum gravity simply reflects correlations between different degrees of freedom within the universe. Many theoreticians have considered candidate possibilities. None have commanded wide assent. I'm not aware of any proposal that a variable like the complexity should be time. However, several things do distinguish it. Among the candidates I know, it is alone a pure number. Second, it is, as I emphasized, many things at once, including intrinsic size. In fact, a common proposal for time is the volume of a spatially closed universe. But in shape dynamics, that is a gauge variable, not a pure number. In contrast, the complexity is, as just reiterated, the scale invariant intrinsic size of the universe. That seems to me better. Another argument for the complexity, absent in all other proposals, is that in the classical theory, it is the scale invariant quantity that not only as the shape potential defines the dynamics, but is also the direction of time. I think this is the place to extend ideas about scale invariant Planck units. Here is a proposal for a Planck time, again, of course, in scare quotes. A key property of the complexity is that it has an absolute minimum. Suppose that we have a shape with higher complexity, which we therefore say has a later time and call now with an uppercase n. Then the Planck time could have the form shown. It is zero at the minimum of the complexity, or the absolute zero of the universe's variety, and increases monotonically with increasing value of the complexity. You will see that it has the same form as the expression for the maximal possible efficiency of a steam engine, which is when the ambient temperature under which it operates is the absolute zero, and the complexity now is the temperature of the furnace. From this parallel with thermodynamics, it is a short step to Clausius's definition for the increment of entropy corresponding to the addition of an amount of heat dq at the absolute temperature T. Here too, we have an inversion of thermodynamic orthodoxy. The increment in complexity does not correspond to an increase of disorder, but of structure. I must come to an end. I initially thought the complexity could be used as time in quantum gravity in a manner that is still conventional in assuming, in line with a causal intuition, that some wave equation evolves a wave function of the universe forward in time from some initial state. For reasons I won't go into here, discussions with the collaborators listed here led me to abandon that approach and rely on the fact that for given n, and without any wave equation, continuous increase of the complexity from its minimum value would take it through all possible shapes that classical solutions which begin at the minimum of the complexity could reach, and because shape space carries its intrinsic metric, would automatically associate relative probabilities with all possible shapes at a given complexity. Tim Kozlowski was particularly important in making that point to me. That fact about the relative probabilities of all possible shapes at a given complexity is reminiscent of quantum mechanics does in the position representation and has an immediate intriguing effect. All singularities that arise when particles get too close to each other in ordinary physics are eliminated. The reason is simple. By its definition, the complexity automatically tends to infinity, even if only two particles get close to each other. But since the complexity is time, such an event is pushed away into the infinite future. It can never be experienced at a finite time. Ultraviolet singularities are a major issue in quantum field theory. Could it be that shape dynamics simply banishes them in this simple way? Tim has also pointed out an even more radical possibility. The complexity depends not only on the relative dispositions of the particles, but also on their number. If the complexity is time, it can be increased either by creating particles and also by adjusting separations. But still, no infinities can ever be experienced in finite time. There cannot be a catastrophic instability that creates a flood of new particles, since that can only be in a never attained infinite future. There's another striking manifestation of shape statistics. Look again at Manuel's two figures, together with two more that I will discuss in a moment, and consider ways the complexity of the shape top left can be increased. The simplest is just to move two particles closer to each other. The created shape won't be a central configuration, but can have the same complexity as the one bottom left. Its structure will be decidedly boring compared with it. It will also violate the cosmological Copernican principle. There will be a distinguished point within it. Of course, the principle is also violated in the central configuration by its center of mass and edge. I don't think that is fatal. It may be possible to create a similar model in a three-dimensional spherical space, analogous to the two-dimensional surface of the Earth. One thing at least is already clear. There are vastly more ways to increase the complexity of the shape top left by innumerable small changes that can be made to all the interparticle separations than by adjusting only a few separations. The near minimal complexity shape top left, whose analog in a closed three-dimensional space should, I believe, satisfy almost perfectly the Copernican principle, that's cosmology's touchstone, will be transformed in virtually all cases, with or without particle creation, into ones that satisfy the principle equally well, that only relatively few, all those close to the central configuration bottom left, will approximate its fascinating structure. Also interesting is the manner in which, despite the voids and filaments, the structure manifests long-range order. Take disks with diameter, say, 1/10 of the full central configuration and place it anywhere except at the edge. The kind of structure it covers is much the same everywhere. That's long-range order. One of the most significant facts about cosmology is that throughout its entire existence, the universe has exhibited long-range order together with fulfillment of the Copernican principle. I suspect the great bulk of all shapes with any given complexity and sufficiently many particles will of necessity have both properties. Now consider the distribution top right, taken from a paper by Michael Joyce and collaborators. Its complexity for the same number of particles is certainly greater than the minimum top left, but less than bottom left. It has a so-called glassy distribution, like that of the molecules of a glass. The universe seems to have looked like that as far back as cosmological theory and observations can determine. It is at least qualitatively like the famous Harrison-Zeldovich fluctuations when they are represented not in Fourier space, but in real space. It gives an idea what the universe looked like before it thermalized and gave rise to the cosmic microwave background. The widely acknowledged success of inflation is its ability to suggest a quantum mechanism that could have generated those fluctuations. Here, the idea that complexity is time directly creates fluctuations with at least qualitatively the same form. In contrast, a kind of distribution through which our universe does not seem ever to have passed is the Poisson distribution at bottom right. There might be something like the thermal distribution I suggested should be typical at the Janus point of a universe with bidirectional arrows of time. It is time for me to end. I will do that with two hints that quantum mechanics might emerge directly from shape dynamics. Let's look again at Manuel's images and recall the argument that the great bulk of the shapes just above the complexity's absolute minimum will come about through many small changes of the interparticle separations. Since, at least here for equal mass particles, the smallest separations are, except for the slight density decrease in 2 dimensions, almost all nearly the same. This will also be true for the slightly higher complexity shapes. You see this confirmed in Manuel's central configuration if you look at it carefully. The smallest separations are nearly all the same. A great early leap to quantum mechanics was Niels Bohr's proposal that the angular momentum of the electron in the hydrogen atom must be quantized in units of Planck's constant. At a stroke, this explained why the electron does not fall into the proton. Might we be seeing a deeper explanation here? At any given complexity, for purely statistical reasons, virtually all the smallest separations will be the same. Just as with Bohr's proposal, you won't find any coincident particles. Do these pictures, freighted with possibilities, point the way to a quantum theory of the universe? I see a chance, the second hint, that they do in the crystalline structure on the left. It looks to me like a realization of one of our panelists, Ted Jacobs' suggestion a few years ago at a conference in Jerusalem to honor Bekenstein's work on black hole entropy. Ted recalled Georges Lemaitre's idea, advanced in 1931, that the beginning of the world should be identified with the ground state of a primeval quantum atom that is highly unstable and divides into smaller and smaller atoms by super radioactive decay. The shape on the left with near minimal complexity certainly looks to me like a primeval atom. Thought-provokingly, its existence owes nothing to the Hilbert space structure of quantum mechanics. It all comes directly from Newtonian gravity made scale invariant. Ted conjectured that Lemaitre's primeval atom would have the absolute zero of entropy, which would thereafter increase forever, matching the ideas proposed first by Feynman and then Penrose. They conjectured that the universe began with extremely low entropy and then evolved to states with ever-increasing entropy and hence disorder. As I have argued, I doubt whether entropy is a suitable concept to apply to an unconfined system, which is what I take the universe to be. And I also think the universe is not getting more disordered. Quite the contrary, it is getting more varied and structured. I see that in this slide as we go from the primeval atom on the left to the extraordinary structure on the right. One final thought. The simplest possible shape is a triangle, and the one with least complexity is equilateral. If complexity and time can increase, both through changes in the disposition of particles and creation of them, Lemaitre's primeval atom is the equilateral triangle. He was a Catholic priest. I think he would like that possible association with the Trinity. For myself, I would look for truth in mathematics. As Hermann Weyl said, mathematics is the science of the infinite. Thank you.
Thank you very much, Julian, for this impressive talk. We will take our 120 seconds now to collect our thoughts and to marry our skepticism with our curiosity, and for the audience to have time to put their questions into the already very packed Q&A. And we will be back after this little jingle is over. So I invite everyone to switch on their cameras, if possible. Okay, thank you very much, Julian, for a wonderful presentation. Very thought-provoking, very vanguard, let me put it this way. I would like to start the discussion with the first question, and that has to do with, triggered by some questions in the Q&A window about dimensionality. So your complexity increase, that is scaling with our normal Newtonian time, is certainly driven by the amount of dimensions that we assume in your framework. Would this complexity increase be a function of dimensionality, of any kind of measure that you can come up with that we can sort of constrain the extent of your picture in how many dimensions we need to operate to match the experience that we see experimentally? And maybe related to this, if I can continue for a moment, related to this, there is, of course, general relativity, right? And the curvature of the space-time dimensionality is related to a slowing down, which if I may use that word here, of the increase of complexity. So how do we deal with that effect by itself?
Well, I'm not quite sure about that. Let me say, Hermann Weyl, I've already quoted, back in about 1930, he wrote a paper where he talked about trying to explain why space-time is four-dimensional, and he came to the conclusion he couldn't. However, I really do wonder whether actually there are arguments for space being three-dimensional. I mean, I think it's right, for example, that the central configurations are very remarkable in three dimensions, and you can have central configurations with other force laws, not the Newtonian one, and they don't come out so beautifully spherically symmetric. I mean, Newton's potential theorem, of which he was immensely proud, is a very impressive thing. So I think it might be. I mean, the central configurations, as far as I think I'm right. We saw it actually in the illustrations. The ones in two dimensions, as you go out to the edge, the density decreases, but in three dimensions, it stays constant out to the edge. And that's a consequence of Newton's potential theorem. So I think there might be something about dimensionality there. But well, with Roger Penrose listening, I'm not going to hesitate categoric statements about space-time and general relativity.
Okay, so I'm sure Roger will tune in. Let's go to Julio next. For the
thanks, Thomas, and thanks, Julian, for the stimulating talk. I must state at the beginning that humbly, I don't think I understood everything you said. So let me put this in the context that perhaps I and others perhaps who are listening might find useful. So to me, the paradox of time in physics is the fact that, laws of fundamental physics seem time-symmetric, but for example, there are, of course, irreversible events in nature that we're witness to. So you started, movingly by honoring the passing of your colleague to begin with, and that seems an irreversible event. In the universe, of course, the creation of big bangs, formation of black holes is an irreversible same thing, in the sense that even if we believe in time and stop time and turn everything that we could backwards, all the velocities backwards, etc., and we make the universe contract, for example, we cannot go back to the same point. And that's something that, of course, Roger Penrose has been arguing for years. So in other words, the time for dissolution of black holes is much longer than the age of the universe in which it is created. So it can go back. So to me, the paradox of time, or the critical point of this ordering of irreversible events that we call time, has to do with this ability. Can we stop, something that we call time, reverse quantities in the universe, and make it go back to something that was at the beginning? Is this reversible in some, sense, in any parameter that we can think of, any property of the universe I can think of? And I guess I was wondering how these ideas fit within your idea of shape dynamics, where you borrow many of the ideas of the conventional Big Bang theories and perhaps rename them and give them a different meaning, like Janet's point, the Big Bang, complexity is time. So how you deal with us in shape dynamics? Is this a reversible universe in some sense? Or is it just like the universe that we think, more conventionally, that we live in, an irreversible one, where the arrow of time is basically imprinted on it by the existence of a singularity, or a Big Bang-like singularity?
Well, I'm increasingly coming to think something which Roger Penrose was sort of at least putting forward as quite a serious possibility. Roger will correct me if I'm wrong, that maybe when we get to quantum gravity, the theory of the universe is fundamentally time asymmetric. It's not time reversal symmetric. And certainly I'm coming more and more to think that way. Now, I come more and more to think that I suspect that consciousness only relies in shapes, and so to speak, in shapes that have a given complexity, and there just are different shapes. And at the moment, we are all in one particular shape now, and let's make the most of it. I'm enjoying talking to you and seeing you all over the world. And that shape just exists. And in some senses, it's sitting there in shape space, and that's just it. And if it's self-aware, well, that may be how it is. I've felt that way for a long time. It was, who was it said, you should see things sub specie eternitatis, the philosopher, come on, my memory for names. Anyway, you should see things in the perspective of eternity. So I would say all the shapes are just there. You know, each one of them in its own way may or may not be self-aware. That's the best I can do.
That's fine, thank you.
Spinoza, of course, is the philosopher I was struggling for.
All right, let's go to Jorge next.
Thank you for the very challenging talk. I have a couple of questions just to understand the formalism, because for me it's completely unfamiliar. The first thing is, how do you define complexity for massless particles? Because we do have massless particles, and they play an important role also in the evolution of the universe. And the second question is more, let us say, philosophical. This increasing complexity apply also to living beings' life, because then that will say something about the evolution theory. Standard evolution theory that says that there is no direction in evolution. But if there is evolution in complexity, and that is the arrow of time, then that will also imply something about evolution of living beings. I would like to hear your opinion on that. Thank you.
I'll do my best. First of all, about massless particles, I should say that the model we're working with at the moment almost entirely just been done with point Newtonian particles, which are assumed to have mass. Actually, you don't even need them to have mass. They could just be all identical particles. And then you would actually start getting close to Einstein's idea of explaining all of physics by just pure geometry, just pure point particles, points. We haven't begun to address questions of the different properties of particles, whether they've got masses or not, their spins and things like that, whether they're fermions and bosons. All of that, I think, has got to come when we move to dynamical geometry coupled to matter. And a lot of the mathematics is existing. I mean, it's part of it is in some of that is in Flavio's book. And if shape dynamics is it going in the right direction, there's a terrific amount of work to be done to really say whether there's anywhere there. Now, about evolution, yes, of course, Darwinian evolution does not seem to be definitely going in one direction. I mean, I read somewhere that we human beings are getting smaller, not larger, because we don't have to work so hard to get food and things like that. However, we do live in a universe which up to now has got much more varied and structured. And if you read an interesting thing, if you read Leibniz's monadology, he says we live in the universe which is more varied than any other possible universe, subject to the simplest possible laws. Now, a few years ago, I happened to have lunch. I had an introduction to have lunch with the man who had just retired as the editor of the Leibniz project in Hanover, editing all his papers. It's a colossal work. They're only halfway through it. And I said to him about my interest in monadology and maximal variety. And he said, well, actually, Leibniz did have a second possibility, not that the universe is eternally more varied than any other possible universe, but that it is getting progressively more varied all the time. Now, we're certainly not, and Leibniz also thought that there were, in every fish pond, there were fishes within fishes and going on forever down, or fleas upon lesser fleas and so forth. And that's definitely wrong. I mean, quantum mechanics showed that that idea of Leibniz was wrong, but certainly the variety in the universe has been increasing from the Big Bang up to now, and maybe it could go on increasing into the distant future. I think that's a possibility.
Okay, thanks. We have Martin next. Could you unmute yourself, Martin? I think you muted yourself. You were unmuted already. We can't hear you, Martin. Just click on the mute button one more time.
Okay,
No.
is it better?
Yes, now we can hear
Oh, okay. Yeah, well, I really impressed by this talk. Julian gave, and his papers certainly are very impressive when you read them. And also, impressive also is the number of people that he cites who have been dedicating themselves to this question over the years, you know, Mach and Dirac and Leibniz and Einstein, Grossman, you know, all the historic figures that we admire and thought about how physics works and what the universe is all about. And, it's really a very impressive approach that he's taken for all these years. It takes guts. It really takes guts to be working outside the accepted dogma of science, and I think he's done that really admirably. The thing that impresses me is that so often when we apply statistical mechanical arguments, thermodynamics and so forth, as is natural for us to do because it's been very helpful, that we run into boundaries that we had absolutely not expected. And this is because of emergence in science, which is always difficult to predict. But there are emerging phenomena that have characteristics which are totally different from anything that we've seen before. And we tend to rule those out by sticking too closely to thermodynamic arguments that we feel wouldn't permit anything as crazy as these phenomena appear. And among those are superconductivity, for example, no conductivity at all, extremely high conductivity, superfluidity, where there's no viscosity. If you argued that ahead of time, as people always did, you wouldn't predict those. They emerge from the complexity of a system and have completely new rules and completely new dynamics. And I'm wondering whether the difficulties that Julian has spelled out here so clearly come from the fact that we don't have any insight on such an emergent phenomenon governing the universe as a whole, where we don't have to worry about friction, we don't have to worry about viscosity, we don't have to worry about the usual things in thermodynamics that lead into trouble, and we have to start all over again from scratch, and that's difficult to predict. On the other hand, I think one shouldn't throw out the possibility. Thank you.
Yeah, well, thank you. Let me just once say about, were you kind saying that I was courageous? In fact, I deliberately went independent to be financially independent, and I can assure you it's much easier to stick your neck out if you're financially independent. Not that I was a billionaire or even a millionaire. I mean, I'm not a great expert on all these fascinating things you read. I did read and enjoy the book by Robert Laughlin, what is it, A Different Universe or something, about all these emergent phenomena. You're much more expert on that particular thing than I am. I wouldn't be surprised by anything, to be honest, in this universe. It's just so amazing. But I mean, and it's effects like that, of course, that make physics such a fascinating subject. I can't really make any more comments than what you've already said, I'm afraid.
Okay, I see that Roger has his hand up. Roger, please go ahead.
Hello, Roger.
Well, yes. No, very impressive, as always. I wanted to raise a point right at the beginning when you were talking about shape dynamics. It sort of rings a certain bell with me, which I wasn't sure was ringing towards the end of your talk. The bell is basically conformal structure. You see, conformal structure is to do with shapes where you're small and big are the same, but the essential difference, as far as I can see, is that you're thinking of spatial shapes and not bringing time into it in the same way, because when you conformally, you stretch the time when you stretch the space. And so the Maxwell's equations are invariant under such transformations. And any massless field has that aspect to it. Whereas the way you're talking, it's mainly spatial. I just wondered what your comment would be on relation to how time seems to be treated in a different way rather than the relativistic conformal way where when you squash the space, you squash the time at the same time. And this preserves the field equations of Maxwell, for example.
Yes, no, that's absolutely right, Roger. I mean, a slide that I had earlier was, in a way, when I suggested perhaps that Einstein had made a mistake, because it was a very fruitful mistake, the way he got to general relativity. But I think there is another way in which conformal invariance does play a very important part in general relativity, and that is in the initial value constraints. So general relativity is like Maxwell's theory, the Gauss constraint. You've got to have some initial data that satisfies the Gauss constraint before you can evolve it and do things with the theory. And in general relativity, the analogous constraints, well, there's three that are closely analogous to the Gauss constraint, but then there's one which is completely different, which is the Hamiltonian constraint. And this really, you couldn't possibly do any really numerical dynamical calculations in general relativity until you have found initial data that satisfy those constraints. And this was where sadly, he just died only yesterday, Niilo Murukku, wonderful relativist, with Jimmy York in the early 1970s, they did find, building on earlier work from Lishnerevich in 1944, how to find a whole lot of solutions that satisfy those initial value constraints. And in that case, the three-dimensional conformal, and it's three-dimensionally conformally invariant, and the key quantity there is not the Virial tensor, but the Cotton tensor, which it's called the Cotton-York tensor. The Cotton tensor was developed, I think, in the sort of about 1900 to 1910, that stage there. So that's where the difference is. And then from there on, you get initial data. So that's basically how the shape, the three-dimensional shape is, what the three-dimensional shape is and how it is changing. That's encoded in that three-dimensional data. And then once you've got that, then you can evolve it and make the four-dimensional space-time. And I think it could quite, I mean, there is a paper that Neil and I and Brendan Foster wrote, Relativity Without Relativity, where we start purely three-dimensionally and in a completely different way arrive first at vacuum general relativity. Then you try to couple a scalar field and you find it's got to have the same light cone. Then you try to couple a one form and you find four conditions. Three of them say it too has got to have the same light cone. And the fourth one says it must be vacuum Maxwell. So there are different ways of arriving at general relativity, Roger. Yes, I just want to say that. So I think in some ways I would like to suggest this could be complementary to all that work that you've done.
Yes, well, GR is certainly not conformal invariant. It has aspects of it. As you mentioned, the Cosmology tensor, but the Virial curvature is, of course, the curvature in 4 dimensions.
Yeah.
And in a sense, it does describe the free gravitational field.
Oh, yes, I don't know. I'm not in any way questioning that, Roger. I think but I do think the fact remains that the solution of the initial value problem exploits 3-dimensional conformal invariance, the 3-dimensional one.
Yes, you do have aspects of conformal invariance there. But it's just that when you talk of shape dynamics, it strikes me as being very non-relativistic in a sense. You're talking about 3-dimensional shapes rather than thinking in terms of 4-dimensional structures, which I mean, it's much more, it's closer to relativistic invariance, because when you change the shape, you unless you change the time at the same time, you lose the speed of light. Of course, it has changed and so on. So,
yes, yes. No, we're definitely trying. We're trying hard, Roger, to be different, and I mean I hope it's a complementary approach, and I mean our aim is to recover everything, all the sorts of things that you've done in the 4-dimensional way, but just arrive at it in a different way, which I think would have, historically could have happened. I mean, I think the fact that Einstein did special relativity before he really seriously got to work on general relativity, it dictated the way he developed his theory, and of course Minkowski was very important. But if Minkowski had not been there, I think it's conceivable that general relativity could have been found in a 3+1 quite different way. I mean, I've certainly written about that quite a bit and discussed it with quite a lot of people, including, well, in particular, Jimmy York and Niilo Murhu, who looked at general relativity not so much as a space-time theory as a dynamical theory. And it's fact their work then that made possible all the numerical work on in general relativity that predicted the form of because they have to do numerical work in general relativity, merging of black holes. You first of all have to find initial data that satisfy the constraints. So when I first started working with Neil 12 years ago, he said, well, you know, these numerical people, they come into the laboratory in the morning and they get the computers to find initial data. And once they've got them, they're away, and then they evolve them for the next week. And then they get these templates for what will happen, what the gravitational waves will look like from mergers. So I think it's a case of complementarity, not in Bohr's sense, but in a way where you balance between a 4-dimensional approach and a 3+1.
Could I take you both to an extreme place, Roger and Julian? Let's go to the event horizon. So how does shape dynamics play out, you know, with the aspect of the Bekenstein's formula, where you have this dimensionality switch between the event horizon and, you know, general relativistic space-time around it? So how does shape dynamics work on these extreme conditions?
Well, here I would say this is going to be probably one of the most really crucial tests for shape dynamics. If we can't, I mean, Flavio has started trying to work with David Sloan on this sort of problem. One thing I mean, and again, here I hesitate to stick my neck out with Roger listening. The thing, a lot of the work on black holes requires a spatially flat space-time, all these wonderful, beautiful structures that Roger introduced, does actually require some notion of what's going on at infinity. And if the universe is spatially closed, I think that may change things. But I mean, it's a long, long way away, I think, for shape dynamics really to get to grips with black holes. But the fact that they have entropy and form is not inconsistent with our basic idea, because when a black hole forms, it's a tremendous clustering of matter, and that would, I think, any way that one would attempt to define a complexity in this situation would increase quite a lot, to say the least.
Okay. Any comments, Flavio?
Can you hear me?
Yes, we can hear you.
Yeah, yeah. I mean, you called me to question, and no, sure. No, just one comment. I wouldn't. Most astrophysicists wouldn't refer to an event horizon as an extreme place, because they can be very mild. It's not like the curvature has to be big, but okay. For shape dynamics, and if we shape dynamics, we understand the dynamical theory of three-dimensional conformal geometry that is equivalent to general relativity in most cases. At least Schwarzschild event horizons are a very interesting situation, because this theory works in a particular foliation, the one in which the extrinsic curvature of your spatial hypersurfaces have constant trace. And these, in Schwarzschild at least, these hypersurfaces are really repulsed by the event horizon. They don't like to go through it. They seem to stack up against it, or in certain, depending on the boundary conditions, they might go through it just a little bit. Anyways, they really avoid the singularity. However, one can foliate this way the interior of a Schwarzschild black hole inside the horizon, and have a description all the way to the singularity, and very interesting things happen. This is an advertisement to my latest paper with David Sloan. It's on the archive. So there, if you want, this theory is, as a Hamiltonian theory, requires something in order to have a full description of a black hole, let's say. And definitely there are unanswered questions there. I just wanted to comment this. But yeah, this is the most accurate thing that I can say at the moment. Further investigation is needed.
Yeah, wow, that's very good. It's a great outlook for the future and job security, I guess. Very good. Okay, let's go to Paul next.
Okay, thanks a lot for the talk. I must admit that I haven't understood everything to a degree that I don't even know whether my question is appropriate that I'm going to ask. And the question is this: if you look at revolutionary viewpoints in physics in the past, then these revolutionary viewpoints were mostly evaluated along 3 dimensions, namely, do they produce novel predictions, or do they explain yet unexplained phenomena? And then, even if they're very successful there, are they able to reproduce the solid results of the pre-revolutionary viewpoint? These are the main variables. Now, my question is, and as I said, I don't know whether it's an appropriate question. How does your new viewpoint fare in these 3 dimensions?
I think, well, certainly, at least as far as Newton's theory is concerned, it just is Newton's theory. I mean, so it's all of Newton's theory. I think what it does do is reveal certain very remarkable properties of Newton's theory which haven't been properly appreciated before, possibly not even by the leading n-body specialists. If we're the main hope, I think, for shape dynamics really to take off is related to those very last slides that I showed, particularly the one with 4 images, because I was hinting there that it's just possible that shape dynamics leads to an alternative to cosmological inflation. In fact, a great deal of my talk came out of a challenge. Pedro Ferreira, the cosmologist at Oxford in the Department of Astrophysics in Oxford, whom Roger certainly knows very well because Roger helped him on Pedro's wonderful book, A Perfect Theory. Back in 2014, Pedro put a challenge to Tim Kozlowski and myself, saying that could it be that Newtonian gravity might suggest an alternative to inflation in cosmology? And that has been an incredibly fruitful challenge. That's what I'd already learned a bit about these total explosions, these extraordinary things or total collisions in Newtonian mechanics. And I've been very lucky to interact with some of the very best N-body specialists in the world, particularly too in Paris. And so I did know a bit about them. And then bit by bit, this idea in both Tim and Flavio, there was a critical trip that I made to Rome about 4 years ago with one idea, and Flavio tested it while I was taking a snooze in the afternoon and found it must be wrong. And that then prompted me to give up the idea which I'd had before, which was really the one to do with when there's a Janus point, and start thinking seriously about the alternative when there's a total explosion or a total collision. And then it's just extraordinary. I mean, those pictures, I don't know what Ted's reaction was because I really picked up this idea from Ted Jacobson's article about entropy and the bit about Lemaitre's primeval atom. I mean, I think it's just extraordinary how those 2 images with which I ended my talk, the one on the left, you really would say that's a primeval atomic quantum atom. And then you get that amazing structure in the one on the right. And so I think it's and it would go through the ones that look at least qualitatively like the Harrison-Zeldovich spectrum. So my main hope for shape dynamics getting confirmation is that we could really make a firm prediction of details which people have not hitherto suspected, and then actually be observed in the microwave background. So I think it's entirely possible, and it's just, for me, it's a wonderful thing. What looks like an outrageous challenge that Pedro gave to Tim and myself. It's kept us happy for 6 or 7 years.
Very interesting. Yeah, I just want to mention that the BICEP people just published a paper. No, they pushed the tensor to scalar ratio by another factor of 2-3 down. So it looks like the first inflation models are excluded already. So let's see what the future brings.
Oh, well, it might be very relevant. Yes.
Yeah, exactly. Yeah. Okay.
Yes.
So let's go to Ted next.
Thank you. Thank you, Julian. As you know, I was familiar with these ideas somewhat, but it's fascinating to hear you talk about them and very thought-provoking. I wanted to make one quick comment and then ask my main question, or express my main concern and phrase it as a question. So the comment is just that actually in modern developments in ADS-CFT duality, which is this holographic formulation of general relativity and string theory being equivalent to a conformal field theory in one less dimension. So there's actually an extremely concrete, rather well supported formulation in the context of quantum mechanics of an equivalence between much of what we consider as standard physics, including general relativity, and a conformal quantum field theory. So that theory it's a shape dynamics theory in the sense that nothing in that theory depends on scale. In fact, you can even vary the scale locally. It's not just overall scale invariant, it's locally scale invariant. So everything the conformal field theory has to say is extremely shape dynamical in the sense that I think you're talking about. This actually is shape in the sense of space-time, not just spatial. It's a space-time conformal symmetry. So I just think that's a very interesting point and observation. And if the driving philosophy is that physics should be, truly about scale-free things, one should look closely at what lessons that holographic duality has to offer. So I don't know if you have a comment on that before I ask my question.
I'm aware of it, of course, Ted, but I don't think I can really add much useful. The only thing I would perhaps add is that Einstein's theory that there are 10 field equations, and 4 of them don't involve time at all. And Karol Kuchasz was somebody who's pointed out that in some senses, in some ways, those 3 the timeless equations in general relativity, in some senses, do contain the whole story, including the time evolution one, which you're probably aware of from Karol Kuchasz's papers in particular. So I think there's hope that there could be a meeting there, but it's quite right. And Roger is absolutely correct to say, you're going against the grain of some tremendously powerful mathematics and things like that. I won't for 1 minute deny that.
Okay, yeah, I should clarify the spirit of my comment wasn't so much that this means that your approach can't be right. I think it could be a different way of formulating.
Yeah, no. I wasn't thinking you were saying that, Ted. No.
Okay, but then so now focusing on this fascinating idea, specifically the role of complexity, the definition of it, the definition of shape space. Almost everything you spoke about relied very, very heavily on point particle mechanics, and much of it even on the specific form of the Newtonian gravitational potential. But physics involves a lot more than that. We think that the basic, as best we can understand physics today, it's about field theories. There are many kinds of interactions. Standard model is complicated. We have general relativity. So it's just sort of, what I'd like to know is, how confident are you and what ideas do you have about the possibility of formulating this basic idea of complexity and, shape space in a way that's compatible with the body of physics that we already know is part of the world? That goes well beyond point particle Newtonian gravity.
Yeah, well, here I think this is where if we're right, there's great scope here for a big research program. I mentioned, but only very briefly, that there is already a perfect analog, a very clear analog of the complexity in general relativity and in the 3-dimensional part. It's the Yamabi invariant. So Yamabi made this conjecture in 1960 that given a Riemannian metric, so plus in, I think it's 3 or more dimensions, there should exist, he claimed that there does exist a conformal transformation that makes the 3-dimensional scalar curvature constant throughout the whole manifold. This is a spatially closed manifold. His proof was found to have a mistake. It was finally confirmed in 1988 by Rick Schoen. And that is, I understand, regarded as one of the great triumphs of 20th century mathematics. It is it's the Yamabi invariant. And it's and Niilo Murukku had a very interesting paper on all lots of wonderful things you can deduce using the Yamabi invariant in vacuum general relativity. Now, in my book, The Janus Point, I conjectured that maybe when you take into account all the known forces and make them scale invariant, there will be a generalization of the Yamabi invariant to include them. Now, I was particularly in the first place interested in just adding a scalar field, because this relates to this very interesting paper that Flavio, Tim, and David Sloan did about continuation through the Big Bang, where you have what's called quiescent BKL, Belaving, Kalatnikov, and Lifshitz, where a scalar field or a stiff massless scalar field or a stiff fluid will stop all those billiard bounces and allow you to get to the true singularity, and it seems pass through to the other side. And so I was very interested in the first place of adding a scalar field. And in my book, I suggested that would be the first step, to have what I called Yamabi plus scalar field. And even better would be Yamabi plus matter. Well, lo and behold, a few months ago, I was talking to Martin Lessoud, who is now in Harvard with Yao, and he immediately looked online and found a paper from 2006, of which I was not aware, where the Yamabi invariant is extended under certain conditions to include a scalar field at least. And that's a paper by Madame Choquet-Brouard, Jim Eisenberg, and one other person. So that's the first step. Now, I would say shape dynamics would be wonderfully well in shape if that could be extended to all the known forces of nature. And maybe you could put that as a selection principle. You would say the forces of nature must be such that there is such a three-dimensional scale invariant that does that trick. So that's the big research. That's one of the really big. So I would say there are two big research projects for scale dynamics. One is to see if it can replace inflation, and the other is to see if there is a Yamabi plus matter. I think that would be very, very encouraging, and it seems it would be closely related to some of the deepest mathematics you can do.
Is anyone working on just the pure general relativity version using the Yamabi invariant to try to explore this Janus point, or initial, what did you call it, the analog of the Newtonian solution with all particles coming out of one point, or
total explosion?
So to formulate your basic ideas just in pure general relativity, has that been developed at all?
No, I'm not aware of it. Something seems to have happened. I'm suddenly, but I can see you. I can hear you, Ted. I can't see you anymore. I don't know whether it was I did something or something, but at least we can continue to. Now, I'm not aware of it, but I'm hoping perhaps the group in Harvard might. I was sort of dropping hints. I did alert Martin Lessoud to the fact that this is going on. So if he's listening, then perhaps he'll start trying to get some people working on these things in Harvard. In fact, actually, I mean, he was telling me that the Yamabi invariant plays a very important role. If I remember right, plays a very important role in the new developments around black holes that. He talked about was it a year ago? Or yes, about a year ago, I think, in an Oxford conference, which Roger went to, and Roger may remember. So, it's out there for anybody to pick it up. And as a good scientist, I'm just waiting to be proved that I'm completely wrong.
Thank you.
Great. I see Enrique has his hand up. Enrique, go ahead, please.
Thank you. No, just a brief comment on that. I think in vacuum jar, if I'm not mistaken, I haven't looked at this in a long time, but the Yamabi invariant on if space is a topologically a three-sphere. Then the Yamabi invariant takes an extremum on the round sphere, and if you create the scale invariant perturbations, then it decreases, or I don't know. I think it increases or decreases the Yamabi invariant. So there is some prospect for fulfilling some of the roles that Julian is envisioning. But I would like to ask a very conceptual question, actually, to Julian, that was hinted in Ted's and Roger's questions as well, which is that there is this preference, in a way, Julian, throughout your work, I think since the end of time, at least, for an ontology that is based on spatial facts, spatial configurations and spatial facts. And there is this tension with modern physics and tension with a lot of how people conceptualize the world, that time has become a more integral part of the geometry, much in par in certain respects with the other dimensions. And in your answer to Roger, you said that you only think of this as complementary to a picture that is based on four-dimensional covariance. You're saying, I wanted to press you a little bit on that. Do you feel like there's no conceptual reason besides trying an alternative to explore the three-dimensional based ontology, or do you think there are good reasons to think of space as somehow more fundamental than time, like you did in your book? I wanted to know your present view.
Yes, thanks. Various things. Can I first of all make an important observation about the Yamabi invariant? In general relativity, just in pure vacuum general relativity, it basically only represents gravitational waves, and quite unlike the complexity, it just has an upper bound and it has no local minima and no saddles. So in that sense, it's completely different from the complexity. However, until we know what happens when I don't think the scalar field has been added or something like that. So that is something that I think needs to be researched. As regards your question about how I think about, I would say that as far as the classical theory is concerned, I would just say that the shape dynamic representation of general relativity is just another way of looking at Einstein's great theory. And I think it highlights that exactly the same thing that you find in the Newtonian theory, is that there is just one extra Hamiltonian degree of freedom, both in Newton and in Einstein, which is not explicable from three-dimensional shape dynamic perspective. And that was actually brought out in the very last paper that I had with Neil back in 2010. I went to Neil with a completely wrong idea, and Neil turned it into a right result. I don't claim any credit for the actual result, it's Neil's. So Neil, I hope you're listening to this and take credit for it. I think so that mystery is there in general relativity, and so I'm inclined to think that I certainly will. I won't take poison on it, but my gut feeling, maybe it's very naive, my gut feeling is that space is fundamental. That it is. Galileo said he that attempts natural philosophy without geometry is lost, and he certainly meant three-dimensional geometry. It's marvelous what's come out of three-dimensional geometry. So I mean, I think quantum mechanics. Look at. I mean, we've barely spoken about quantum. Look how time stands out like a sore thumb in quantum mechanics, completely different from the other observables in quantum mechanics. John Bell always said that the position representation is what counts. That's ultimately where it is. He says that the end result of any observation is always relative positions of objects, even if it's ink on a computer printout. So I think that my own feeling is that the reality is in three-dimensional space, that it's structures within three-dimensional space. It is very wonderful how then Einstein gets his four-dimensional theory, but I think that might just be a historical accident.
That's fascinating. Let's go to Elizabeth with a few Q&A questions from the audience.
Yes, so we have the most voted question from Terry Bollinger. And he's asking, complexity is information. Information is entropy, and entropy increases with time and drives it by Boltzmann. In what way does shape dynamics complexity increasing differ from entropy increasing?
I think that when you consider the whole universe, entropy is just the wrong concept. I mean, I did actually do quite a bit of studying the history of thermodynamics, and I defer to no one in my admiration for Sadi Carnot, Lord Kelvin, Rudolf Clausius, Robert Maxwell, Ludwig Boltzmann, and Gibbs. Fantastic. And thermodynamics is just marvelous. It covers so many things so wonderfully, and it's a fabulous theory. But the whole wonderful theory was developed by analogy with steam engines, systems in a box. Once you take the box away, things might be very, very different. So I just think there's a wonderful analogy with Kepler's work. Kepler was hugely impressed by observations of the comet of 1577 that Tycho Brahe had made. And Kepler said his observations showed that comet must have gone clean through all the celestial spheres that were meant to carry the planets. And he said, this changes everything. And he said, henceforth, the planets must find their way through the void like the birds through the air. We must philosophize about these things differently. So when you take that box away, it's like that comet destroying the celestial spheres and stimulated Kepler. And by the way, Kepler's work is just an absolute miracle. How he was the first human being, just like Roger knows how to wander around in space-time, Kepler was the person who knew how to wander around in his mind's eye in the solar system and look at everything he could see from wherever it was. It was just fantastic. And that's why I think, forgive me, Roger, that's why I think space is the more important thing. The dispositions of things in space are what really counts.
Ted has a comment?
Yes.
Yeah. Ted, do you want to chime in?
Oh, I just want to make one comment on it. This question, it's a great question, and I thought of a similar question while I was listening to Julian. I wondered whether it couldn't be that the increase of complexity and the increase of entropy are both correct ways to look at it. And what's going on is that, like, the complexity is a property of a single instance, and the entropy is a property of the ensemble. And so that somehow they're not in contradiction, those views, but maybe they're actually different ways of talking about the same thing.
I would put it slightly differently, Ted. First of all, I would say what we find is there definitely is thermodynamic behavior. I couldn't go into it in all details. No, it all comes out of the Lagrange-Jacobi relation. Instead of taking Liouville's theorem, which Gibbs did as the foundation of statistical mechanics, I think one should really use the Lagrange-Jacobi relation, which leads to the Virial theorem. So there are no properly isolated systems, but so the Lagrange-Jacobi relation says that if the energy is non-negative, you will get this Lyapunov variable, and you cannot have Poincare recurrence. And if you don't get Poincare recurrence, you haven't got thermodynamic behavior. However, the Lagrange-Jacobi relation allows subsystems to have negative energy, and then they will transiently, they will virialize. And I would say a virialized system is actually what is ultimately the thing that is always thermodynamic. It's basically sort of approximating Poincare recurrence while that is happening. And therefore but I think you're quite right that I showed that slide that David Sloan loaned me of focusing, but what you really see, that's why I emphasized the difference between what the demon sees. The demon the demon is sitting in one microhistory. He's not sitting in the ensemble. So the demon in thermal equilibrium just sees a swarm of bees the whole damn time. Nothing interesting happens. You put that same demon in a Janus point solution. He's got to be on one or other side of the Janus point. And it seems literally as if that universe, as I said, came phoenix-like out of fire, and is just getting more and more interesting as time goes on. So I think that the real way ultimately to think about these things is what the demon sees in the two different cases. And they're just completely different. They correspond to the difference between confined and unconfined systems, and in terms of statistical mechanics, between systems that have a phase space with bounded Liouville measure or unbounded one. And by the way, when Boltzmann was struggling to meet Zermelo's very sharp questions, and Zermelo was relying totally on the Poincare recurrence, Boltzmann did say, perhaps the universe is not essentially a confined system. It may not have a bounded phase space. But obviously in 1896, no way could Boltzmann make many useful conjectures about the universe. And also, I would say it may be a pure historical accident that thermodynamics was discovered 80 years before the expansion of the universe. Put that the other way around, would it all have developed inside a box?
Yes, because railroad locomotives have boxes.
Yeah, they've got to, otherwise the thing comes to an end, stops running.
I just have one quick comment in reaction to that. I think one can consider the concept of entropy without considering thermal equilibrium. And what you've been emphasizing is that the notion of thermal equilibrium may be just not relevant for the fundamental description of the universe in its whole, and I agree, but nevertheless, the concept of entropy could be still, and I think is still meaningful. And then this apparent dissonance between our idea that entropy is increasing in the universe versus you saying, no, it's not about entropy, it's complexity that's increasing. Just still advocating that despite the non-existence of thermal equilibrium fundamentally in the universe, that could still be true. They could both be true statements, because they're referring to really different things. One an ensemble property and one a particular property.
Well, I wouldn't actually say it's an ensemble property, Ted. I would say it's more that there are lots of systems in which you can say there is definitely entropy is increasing. These are systems that come into existence with a low entropy. They're not yet virialized. They come into existence. They virialize. That I would say is they've developed entropy. And then, just as Klaus said, you can add up all those things and say that's an increasing entropy of the universe. But I think that's hiding the really fundamental thing, is that the complexity of the universe is actually increasing. So I think probably we actually agree, Ted, it's not a fundamental difference.
Okay, thank you. The next question is from Tori Bollinger and Parth Patil. You added the non-standard concept of vanishing energy to your thermodynamic model to get your direction of time to emerge. How do you justify that, and what is negative energy?
First of all, I don't think hang on, let me be clear. I don't need zero energy to get those bidirectional arrows of time. The energy just has to be non-negative. So it is, as long as the energy is not negative, so it can either be zero or it can be positive, then you will always get those bidirectional arrows of time. And that, if I may, and I've made that, it was in the slide, that was the very first qualitative result discovered in dynamics, Lagrange, 1772. So I would say actually a possible very different way of thinking about entropy of the whole universe was sitting there since 1772. And then it was that was in the three-body problem, and then it was extended to the n-body problem a few decades later by Jacobi. So it doesn't rely on zero energy. The reason why zero energy is interesting is that if you take away, so if you've got Newton's absolute time, you can have an initial configuration and then a slightly different initial configuration. And if you say that the amount of time that has elapsed different in Newton's absolute time, then you'll get all sorts of different energies and you'll get many different solutions. So the only way to avoid this, it's a conflict of the principle of sufficient reason of Leibniz. You can't understand why you could have all these different energies. So the only way of getting around that is to say that the energy is zero. And that follows very naturally from saying there's no absolute time.
Okay, thank you. The next question is from Mario Alvarez. Do you think there are plausible explanations, alternatives to Weyl's curvature hypothesis according to the symmetry?
Sorry, which was the hypothesis?
Weyl's
wild curvature hypothesis.
Hypothesis, I think.
Oh, the Weyl. Oh my goodness. Now, I mean, in Roger's presence, I'm not an expert on that. Sorry, Roger, can you say precisely what the conjecture is?
Well, the Weyl curvature hypothesis was just a statement that initial singularities had to have vanishing Weyl curvature. Well, these.
Yeah. Wait, thank you. Yes. No. It's a bit. Yes. No. Thank you very much, Roger. Yes. No. I think this is actually where we get very close, though I would see it perhaps in the three-dimensional conformal sense, Roger, than there, because I think this might be a realization of your conjecture that the universe becomes very uniform at the Big Bang. I mean, if the n-body problem is any guide, you saw that absolutely explicitly in those that last slide I showed that Manuel made of the what I called Lemaitre's primeval quantum atom. So I think that might be there.
I mean, the Weyl curvature hypothesis was to distinguish the nature of the singularity in the Big Bang from those that you get in black holes. In black holes, you get wildly diverging Weyl curvature, and that's where the entropy is going shooting up. Whereas in the Big Bang, the singularity seems to have been one in which the Weyl curvature was zero. So you don't, that's basically the Weyl curvature is describing the gravitational degrees of freedom. So the gravitational degrees of freedom, this is just observationally.
Yeah.
In the Big Bang, we seem to see a situation in which these degrees of freedom were not activated.
Yeah.
I don't see how that relates to the point of view you're talking about. I mean, it's a very remarkable fact that the singularities in the future seem to be extremely different from in the past. And I was only making a hypothesis to say, well, we don't know why, but that seems to be the situation. My current view is a very different one because it comes about through the conformal cyclic cosmology model, where you have to have, if you want to have a regular Big Bang, conformally regular Big Bang, it has to have vanishing bow curvature. Well, that's not quite true, but more or less true.
Yes.
You're just future.
No, I'm back. I've caught up to speed now, Roger, with your reminding me of it. Yes, and I quite agree. All I would say is I think, I mean, basically, what you were so struck by was that gravitationally, the universe looks to have been very, very uniform at the Big Bang, correct?
Where the gravitational degrees of freedom were just not activated.
Yes, yes. Well, that is actually what happens in a total collision, because the forces between the particles just disappear, and it's all just, the whole universe is just forcing all the particles together to collide at the center of mass. And as you saw in those pictures, the shape becomes more uniform than any other possible shape that it can have. And certainly if you're going to the one that has the greatest uniformity. So I would say that the Newtonian Big Bangs are an absolute perfect confirmation of your conjecture in general relativity, Roger.
Well, I'm a little bit confused by your picture. I mean, when you have a collapse to a single point, that's a very special situation. And in general, it wouldn't do that.
But here my point is that size is gauge in shape dynamics, and you just have to look at the shape. So as you follow the shape towards the total collision, you find the shape just becomes uniform. It becomes a central configuration. And that's
only with a structural collapse when it's focused to one point. The general is more irregular, and magnifying it out wouldn't help it at all. I mean, it's
well, but if magnification is just gauge, all you're interested in is shape.
Well, I don't see why the shape doesn't get wildly complicated in the collapse.
Well, it just doesn't. This is one of the really great results of n-body theory. There's a really great paper from 1918 by Jean Chazzy, who worked in Paris, who showed this thing, and this I mean, it's a tremendous work, which I think is hardly known in the relativity community, but it's very well known among the n-body specialists.
I see that. I mean, it must be a very special situation. In general case, you won't get that.
It's, of course, a total collision is a zero measure solution, Roger, but the reason why we looked at them is because we wanted to see whether Newtonian theory, when we could mimic what happens in general relativity, which is something like a Big Bang, what that would tell us. And when we looked at that, we find that it's just unbelievably uniform.
Well, those sound to me like very special solutions. Generic case, you wouldn't get that. I mean, I don't think GR and Newtonian is that different in this respect. I mean, in GR, it's much worse because you get these crazy looking, well, we don't really know what happens in general, but you have these BKL sort of situations which are utterly wild.
Well, this is where we put our hope on the quiescent case, when you have a massless scalar field or a stiff fluid, because then there's only a finite number of bounces. And at least this is through the Big Bang paper of Flavia and Tim and David Sloan, where there's hope that wild behavior is tamed. I mean, if that's really in the right direction, there's a great deal of work to do, but it certainly works in Bianchi 9. And there was a paper in 2002, I think it was, Flavia, Randall, and who was the other person, Flavia? who proved that the quiescent Bianchi the quiescent BKL, that it does become quiescent for analytic solutions.
Can't be just GR. There must be some other fields which are put into the.
Yes, it's with a stiff fluid or a massless scalar field, Roger.
Well, I think it's. Never mind. Let's not talk about it. I mean, I don't see you're going to get that. Certainly not in vacuum. That's your model.
No, you're quite right. It's not in vacuum. No. But there is matter in the universe.
Well,
Okay,
There is
so-
Randall and Anderson, just to.
Sorry, can you repeat, Flavio?
Yeah, the paper is Anderson and Randall, the one that on BKL with quiescence. Just
Okay,
bibliographical note.
So we will go now for the last question from Pablo Daniel Cisterna. Do you have a hint on how shape dynamics could solve the measurement problem in quantum mechanics?
Yes, I've nothing if not sticking my neck out. Well, first of all, John Bell years ago said, when did the first collapse of the wave function happen in the universe? Could it only happen when the first PhD student had got his doctorate or something like that? George Ellis thinks, collapse is just, that it happens somehow sort of spontaneously. If this is going in the right direction, I would just say that's the wrong way to think about it. There are just shapes which have different complexity, and conscious experience is just sitting in those shapes with a given complexity, and it will look like the universe has taken a definite shape. I mean, if you take standard Schrödinger evolution in the position representation, I mean, you would find probabilities for different configurations of the system at a given time. It tells you the probabilities you will expect. So what I proposed is just saying, so this intrinsic metric which exists on shape space, it's there, it's a built-in intrinsic structure, this natural metric just gives you what are the relative probabilities of all possible shapes. And they look jolly interesting, as you saw in that final slide. And as I look at you all here, I see a changing shape, I experience it, and I think that's what the universe is like. And I'm beginning to suspect there just ain't no collapse. It's just that we happen to be in different shapes. Carpe diem, make the most of it. It's been very nice to talk to you all. And perhaps on that cheery note, we should stop.
Exactly. On that note, yes. Thank you, Julian, for your wonderful presentation and the very inspiring thoughts and insights. I think there is a lot of exploration space in front of us.
Yes. Well, thank you very much. It's been a great pleasure. And I do hope soon that my daughter who lives in Buenos Aires will be able to travel back home and see me here.
We hope so too, yes. So thank you very much, everyone. Thanks to the panelists for being here, for tuning in, for your time. Great discussion. Thanks to the audience for sending excellent questions. And please be so kind once we end this live stream to fill out the survey form that will be shown to you in the web page afterwards automatically. And I would like to announce the next Golden Webinar, which will be given on October 16th by Philippe Longnon, who is a professor of geophysics and planetary science at the Paris University, and he will be telling us about Insight on Mars, more than 1,000 sols, which is Mars days, of seismic discoveries. So I hope you can join us then again. Until then, please stay safe, stay healthy, and until the next golden webinar in astrophysics. Bye, everyone. Thank you so much.
Goodbye.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Thank you very much.
Bye-bye.
The after party link is in the separate email.